All right, good morning, folks. We're going to start section 4.2 today, which is called implicit differentiation. In order to understand implicit differentiation, we're going to start with a simple opener. We're asked to solve for y, then find the derivative of 2xy plus 5 equals 0. Again, when we look at this problem, think about why I'm asking you to solve for y. Up until this point, even on your test yesterday, all we've been asked to do is find derivative, whether it's y equal, s of t equal. What we've always had the dependent variable expressed explicitly in terms of our independent variable. So we don't know how to find the derivative as is, so we have to solve for y in terms of x first, then we can find dy dx. So I'm going to solve for y. I have 2xy is equal to negative 5. Solving for y, I'm going to divide everything by 2x. Now I have y in terms of x, and I can work through finding our derivative. But if we think about everything we've done prior to this, we know that in system void quotient rule, I'm going to rewrite my function. And thinking about, I can rewrite it as negative 5 halves x to the negative 1. So I'm looking at just a simple constant multiple rule using our power rule as opposed to our quotient rule. So I can find dy dx to be negative 5 halves times negative 1, 5 halves x to the negative 2. And rewriting, I have my derivative then as 5 over 2 x squared. All right, so we found our first derivative dy dx to be 5 over 2x squared. But now I'm going to introduce you to implicit differentiation. So when we use implicit differentiation, the main difference visually is we're no longer seeing the function expressed explicitly, meaning y equal. Right, so to use implicit differentiation, we can kind of jump right into our derivative. The key, though, is we need to remember y is a function of x. Right, we just showed that y is a function of x here, so we have to remind ourselves that y is not just the same as x. Right, y is a function in terms of x or expressed in terms of x. So I'm going to rewrite our original problem. 2xy plus 5 is equal to 0. The nice thing about implicit differentiation, it neatly avoids us having to find y first. Right, so I can jump right in. But when I think of y as a function of x, I see I have a function x times another function in terms of x, which makes me think product rule. So if we think of this as the first quantity and y is a function of x, you're going to hear me say that 100 times today, y is a function of x. We see two functions in terms of x being multiplied, so we're going to go into product rule. Product rule tells us first quantity times derivative of the second quantity. But again, y is a function of x, so we can't assume the derivative of y is 1, right? We just proved over here it's not. So we have to think y is a function in terms of x, so I'm going to take the derivative of y with respect to x plus second quantity times the derivative of the first. We have derivative of a constant goes to 0, derivative of 0, 0. Right, so there's my calculus move. Everything else is going to become algebraically solving for our derivative dy dx, but at that point, this is where I pause and I ask myself, 10-second checks, right? If I don't have dy dx show up at this step, it's never going to show up. I'm never going to get to the derivative. So I'm going to just start to simplify. I have 2x dy dx plus 2y equals 0. But again, I encourage you, after you make that first move of calculus, double check. Do you have dy dx on your paper? If not, you're never going to get it created. So really check that you have that first derivative, derivative of y, is not just 1. We can't assume it because y is a function of x. So I'm going to solve for dy dx using my algebraic brain. I have 2x dx dy, or 2x dy dx is equal to negative 2y. Solving for dy dx, we'll bring it over here. I have dy dx. I'm going to divide everything by 2x. I get negative 2y over 2x. And my derivative then is negative y over x. Now, at first glance, they don't seem to match, right? We found our derivative explicitly, 5 over 2x squared. Now we have derivative negative y over x. But we're going to check this because we know what y is already equal to. So I can take my derivative dy dx, and I can substitute in what we found earlier when we solved for y in the opener. So we found dy dx. Again, I'm substituting in what we got for y earlier is the opposite. I have a negative 5 halves x to the negative 1, all divided by x, which becomes dy dx. We have 5 over 2x. Dividing by x is the same as multiplying by the reciprocal. So I get dy dx then is equal to 5 over 2x squared. And regardless of our approach, we end up in the same spot. Both of our derivatives are 5 over 2x squared, so we can prove that implicit differentiation works. It's a check.